Truck frame rails are fundamental to vehicle structure, providing the backbone for mounting components and supporting loads. Unlike beams, frame rails are constructed in a channel shape, which offers both strength and flexibility. The channel consists of a vertical web, which is the widest part, and flanges that extend from the top and bottom. Understanding these basic elements is crucial for anyone involved in truck design or maintenance. The height of the web is measured vertically, and the flanges play a key role in distributing stress. The dimensions of a truck frame rail channel are defined by outside height, inside height, and material thickness. Outside height measures from the exterior of both flanges, while inside height refers to the distance between the flanges on the inside of the web. Material thickness is calculated as the difference between outside and inside heights. Every piece of steel used in manufacturing has a cross-section, or profile. The profile determines the item's section modulus, a key factor in structural strength. The shape, represented mathematically, is an input to determining the rail's resistance to bending. This concept is fundamental in truck engineering, allowing for comparison between different rail profiles and ensuring the right selection for each application. The image shows frame rail channels in various configurations: the parent rail, shown in yellow, insert, shown in red, outsert, shown in green, and subframe, shown as blue. Each configuration serves a specific purpose, such as increasing strength or accommodating additional equipment. Most truck components are mounted off the side or web of the channel shape. Drilling holes through the flanges is strongly discouraged, as this can compromise the rail's structural integrity. Manufacturers often place warning labels on the frame to caution against welding to the flange. However, some bodybuilders weld subframes to the rail flange to increase strength, especially when mounting equipment. While not manufacturer approved, this practice is common in certain applications. Frame rail sizes vary depending on the truck's duty class. Medium-duty truck rails, found on Class 6 and 7 chassis, typically measure 9 and 7/8 inches or 10 and 1/8 inches in height, with thicknesses ranging from 1/4 to 3/8 inch. Heavy-duty chassis use larger rails, such as 10 and 5/8, 10 and 3/4, 11 and 5/8, or 13 and 3/8 inches in height, with thicknesses up to 1/2 inch. Outserts must be one size larger than the parent rail, and not all manufacturers use them. For extremely heavy applications, a combination of outsert and insert may be used. The profile of a frame rail is characterized by its height, width, and thickness. Multiplying these dimensions produces the mathematic term for section modulus, a value stated in cubic inches. This is a critical industry metric for assessing the strength. For example, a 10 and 3/4 inch rail can be represented with a value for section modulus of around 17.8 cubic inches. This value allows engineers to compare different rail profiles and select the most suitable option for the intended application. Section modulus alone doesn't determine capability. Material strength must also be considered. Steel strength is reported as yield strength, measured in pounds per square inch. Yield strength is the maximum stress a material can withstand without permanent deformation. The combination of profile and material strength results in the resistance to bending moment, or RBM, measured in inch-pounds. Comparing two rails with identical section modulus but different material strengths demonstrates how RBM can vary. Frame strength is a crucial safety factor, and the requirements vary by application. Most sales tools will use combinations of components to direct the specification toward a qualifying rail, but the actual analysis is performed internally once the order is submitted. Common triggers for increasing the rail during specification are listed here. When in doubt, it is best to communicate with engineering regarding the need ahead of ordering the chassis in an effort to avoid hidden upcharges. The weight of a frame rail is calculated in pounds per inch for the rail pair. Adding inserts increases the tare weight, which reduces payload capacity. Overspecifying rail material can lead to unnecessary weight and decreased efficiency. Most sales tools cannot perform a full frame strength analysis, so collaboration with engineering is essential. They will identify underspecified chassis and provide solutions. Overspecification is rarely scrutinized. Knowing how to balance strength and weight is important for optimal vehicle performance. Ground height is a crucial aspect of vehicle design, representing the distance from the ground to the top of the frame rail. This measurement varies at the steer and drive axles. Rear ground height includes the drive tire's static loaded radius, or SLR, suspension ride height, and frame rail height. If SLR is unknown, half the diameter of the unloaded tire is a close estimate. Tire and suspension data are available from suppliers or sales orders. Calculating the front frame height is challenging due to influences of the front spring height, steer axle drop, and shimming. Shims are used to level the frame, and the slope or levelness is referred to as rake. By subtracting frame dimension at the steer axle from the same point at the rear axle, the difference in height is determined. Dividing this difference by the wheelbase yields the percentage of slope. Engineers correct rake issues to meet design standards, as excessive rake can cause ride problems, vibrations, and load shifting. The process of creating the hole drill pattern is essential for efficient assembly and accurate placement of parts. Engineers use computer-aided drafting, or CAD software, to define component structure and location. Frame drill locations are specified in the bills of material, ensuring components are ordered and available at the build station. Coordination of the parts and subassemblies begins as soon as rail drilling data is sent to the vendor. Truck manufacturing engineers prepare frame drill data by accounting for all component locations. A reference point, known as the 00 station, is used to define drilling locations, often originating at the center line of the front axle or the frame's front, depending upon the OEM. Dimensions can be communicated using either metric or customary units of measure. Frame processing occurs weeks before chassis assembly, making timely data transfer critical. Last-minute product changes impacting hole patterns are not possible once processing begins. Rails arrive at the factory with pre-punched holes for each specific chassis. An identification system allows manufacturers to track each chassis and ensure components are matched correctly. This process ensures each rail is ready for assembly, minimizing production delays. Material thickness determines whether holes are punched or drilled, with thicker rails requiring drilling. Drilling is more labor-intensive and can result in increased cost. Design engineering groups are assigned to specific chassis regions, each responsible for product definition. Requests affecting multiple regions are routed to the appropriate group for attention. Oversights can lead to missing parts or interference during assembly. The frame regions are loosely defined as front frame, under cab, center frame, rear frame, and end of frame. Each region contains specific components and responsibilities. Some chassis regions, like under the hood, are congested with components, while others are less populated. Regions 1, 2, and 4 are well defined, limiting opportunities for optional components or special engineering. Region 3, the center frame, offers the most variability, especially with longer wheelbases. This area is covered by drive lines and cross members, leaving the exterior free for customer components. Understanding region complexity helps optimize chassis design. Even with lower complexity, the back of cab to rear suspension is where engineering fits air components. As such, noticing a lack of componentry does not guarantee the area to be available to accommodate customer needs. Many OEMs have methods for communicating requirements for clear frame areas, which should be used when beneficial. Upfitters often move components to accommodate customer requirements, but this can lead to added costs, system modifications, and delivery delays. Collaborating with engineering and clearly defining requirements prior to build ensures the chassis arrives ready for intended applications, minimizing trade-offs. Cross members are structural elements added to frame rails to maintain alignment, provide rigidity, and resist twisting. They also support key components like the engine, cab, and suspension. The placement and style of cross members are determined by application requirements and chassis design. Cross-member spacing is regulated by maximum distance requirements, stated in inches. An intermediate crossmember may be unnecessary if a center-bearing crossmember is required. This fluid interaction makes predefining the center frame challenging for design teams. Crossmember styles vary by truck class and manufacturer. Class 4 through 7 trucks and some Class 8 chassis use one-piece crossmembers, typically formed from metal. Other styles include assemblies of gussets and channels with 3 or 5 pieces or combinations of 2 crossmembers back-to-back. The choice of style depends on application requirements and desired strength. Slotted or adjustable crossmembers compensate for rail thickness, allowing a single crossmember to be used with differing rail configurations. Slotted crossmembers use a 5-piece assembly with upper and lower gussets on each side. Some manufacturers maintain a constant outer measurement, requiring narrower crossmembers when inserts are used. Others keep a consistent inner measurement, allowing a single crossmember width for all instances. Some components, including crossmembers, are added to the rail before frame paint. The subassembly goes through the paint booth and drying oven as a unit. After painting, the chassis enters the main assembly line, gaining components at each station. Cabs and sleepers are built as subassemblies and installed as units. Timing is crucial, as cabs and sleepers are built and painted days before frame rails are assembled for the same chassis. Rails arrive at the factory pre-treated, usually with prime paint. Some manufacturers offer additional treatments, such as zinc phosphate, e-coat, or powder coating. These treatments protect against road salt, chemicals, and rust, adding longevity to the rails. Galvanic corrosion occurs when dissimilar metals contact each other, so treatments are important for quality and durability. The rail vendor applies treatments after holes are punched or drilled. Vendors play a key role in delivering quality rails that meet manufacturer standards and application requirements. Zinc phosphate is a chemically produced coating resistant to flaking as it modifies the rail's molecular structure. Typically sprayed onto rails, it slows paint disbanding and is resistant to galvanic corrosion. Selecting appropriate treatments is essential for long-lasting frame rails. This non-conductive coating is an important option for enhancing rail durability and should be considered when selecting frame treatments. E-coat, or electrocoating, uses electrical current to deposit paint on the rail. The rail is cleaned, pre-treated, dipped in an electrocoat bath, rinsed, and cured in an oven. Dipping processes have rail length restrictions, while sprayed products do not. Powder coating uses a dry powder spray electrostatically applied to the rail. The powder is attracted to the charged rail, resulting in excellent coating with minimal waste. Baking completes the curing process. Frame fasteners are typically bolt and nut style or huck bolts. Bolts are torqued using a wrench and are considered the most serviceable option. However, vibration during truck operation can cause nuts to loosen, leading to rail failures. Manufacturers publish guidelines for retorquing intervals, usually every 120,000 miles or annually. In harsh applications, this interval decreases. Proper maintenance is essential to prevent failures. Discuss retorque intervals when bolts are used to ensure proper maintenance. Huck bolts are installed using a proprietary instrument calibrated for clamp load, not torque. Clamp load is the tension applied to fasteners like Huck bolts during installation. Unlike torque, clamp load remains constant and doesn't require maintenance. This concept ensures fasteners stay secure, preventing loosening due to vibration and improving frame reliability. If component relocation is needed in the field, the Huck can be cut off and replaced with a bolt. Remember that rail warranty is administered by the OEM, not the upfitter, so decide what is right for your customer. Truck frame rails are the backbone of vehicle design, providing strength, flexibility, and support for all components. Understanding channel shapes, profiles, section modulus, RBM, and material treatments is essential for designing a robust chassis. Collaboration with engineering, proper maintenance, and clear communication with upfitters ensure optimal performance and longevity. By following best practices and industry standards, manufacturers and builders can deliver high-quality trucks suited for a wide range of applications.